Mary, you're muted.
Okay, so I'm talking about the student cluster competition, which is held annually. And this year, last year we had a team that participated and it ended up being virtual. So I'll talk about that for a moment. And my video is on. Can you guys see my talk?
Yes, we can.
Okay, great. So let me get back into moving. So at the student cluster competition, the teams are challenged to run several HPC applications on a cluster that they've typically built and brought to the meeting. But this year, because of the virus, the coronavirus, we had to do it virtually. And so all the applications had to run on Microsoft Azure using the Cycle Cloud portal. And most of the team, they didn't meet in person. They have to run within a strict budget, $2,500 during the competition. So the students ended up focusing on cost per flop. So it's a different kind of environment than the typical SCC where you bring your cluster, you work in a booth, you're out on the exhibitor floor, and you get to know each other. And the focus is on power per flop. And so part of the challenge is the students have to learn all aspects of high performance computing, parallel concepts, CPU, GPU, and now they added in cloud computing. So learning how Azure worked, how to use the tools on Azure, and optimize how you're going to run things on Azure. This was a lot of fun. And I just want to share some of those experiences that the students had. At the end of the day, after a lot of work, we decided to use one kind of VM for certain applications using the EPIC architecture here or ND40 NVIDIA GPUs. So the key was using a flexible software stack, which is a really important lesson. We learned how to use Cycle Cloud templates and chef recipes to build a VM customized to each application. And we additionally customized it using SPAC. And we use SPAC to load application software after the VM was launched. And the VMs, we ended up picking different VMs depending on the application and how many cores we wanted to run for a particular test case. Keeping in mind that we had to also calibrate every VM based on how much it would cost. We only had $2,500 and you can suck away that money pretty quickly if you're not watching it. This is an example of the Cycle Cloud portal where you list all your machines and then you watch them launch. You can observe how it's launching. But there were several tools provided. One was a Ganglia display for all of the teams showing their spend rates, and also a tool from the Azure portal where we could also monitor our spending, but those weren't fast enough. So my students developed their own cost monitoring tools. This is an Excel spreadsheet. This is an output that we use the CLI provided by Azure by logging into a terminal on the machine we launched. And then we also took that data and incorporated into a spreadsheet where for each of the applications, and there were 7 because we had a mystery app, they put in the time they thought they would launch it, how much they would spend. And towards the end, as we got down to hundreds of dollars, this was an interesting predictor tool. And so just to summarize, this is the Grafana display that they put together where all the teams were listed, all of the applications and the progress of each team. We watched these through the day. And my team would look at this and go, boy, how did Tsinghua University get 300 teraflops on HPL? And then they would try to go better. But we did all right. We came in 4th overall out of 19 teams, which is pretty good for a first-year team. And Tsinghua took first place on every benchmark application. And looks like I made just about my 5 minutes. So they did really well. They were an order of magnitude faster than any other teams, but we were proud that we finished most everything and learned a lot. And the team had a great time learning how to use cloud computing. And again, we've been selected to participate this year at SCC21. So thanks to the committee for allowing me to speak. I appreciate it. And that's my talk.
Oh, thank you so much, Mary. That's really cool. It's great to see student engagement like that.
Yes.
Next, we'll turn to Hakim Weatherspoon at Cornell, Exotanium X-Spot. And Hakim, go ahead and take over.
Great, thank you. So my name is Hakim Weatherspoon, and I'm the
a professor at Cornell. I'm actually a visiting professor here at University of Washington as well. But I'm also the CEO of, can you guys hear me? Okay.
Yep.
Okay, great. So I'm also the CEO of a company called Exotanium. Okay, so I'm gonna talk about how to use the spot market. So this is reliably running stateful application containers in cheap spot markets. Okay. So, and just a little bit of background, to start with another professor, Robert Baronese at Cornell, and then our former student, Ziming Shen, who's the main person with the company. So the key here is with the cloud infrastructure as a service cloud, it's on demand, unlimited resources, and it's pay as you go. But the problem is that businesses before the pandemic were spending a lot of the revenue, and today is 50% or more of the revenue is going to the cloud. So Amazon, Google, Microsoft love it. Businesses is a bit much. The spot market is 10 times, up to 10 times cheaper. The price changed dynamically, and you can see here the price change over time. But the key here is it's unreliable. If somebody's willing, essentially, to pay full price, then they'll kill your application that is paying a much cheaper price. So anything that is stateful, you would never use the spot market for, because it's going to die, right before it finishes. So if it's a simulation or something like that, you would not use this for that. There is a warning, but it's only a 2-minute warning, so not sufficient to do anything with. So the goal of what we want to do is we want to be able to reduce your cost of using the cloud by using the spot market, but we want to improve the reliability. So it's as if you're not using the spot market at all. We don't want you to have to change your application at all, and we want you to be able to get good performance. Okay, so the key of what we're going to do is we're going to live migrate your application. It's a game of whack-a-mole from this cheap, unreliable environment to a more expensive, reliable environment. And the overall effect will be to reduce your costs, but have great performance. So this is an animation that shows that, it's just like a VMware vMotion. So you're just going to migrate from on-demand to a spot instance and back. But there's a problem. You don't have access to the underlying hardware. So you as a user are not able to do this. The cloud provider can. But there's a solution that we have in all computer science with another level of indirection. And so we're going to do nested virtualization. Instead of starting an operating system in your application, we're going to start another virtual machine monitor. Okay, so within that virtual machine instance, we'll start another virtual machine monitor. This case is called Zen, and then we'll start your application. And the advantage of this is we, in some sense, have created a thin shim layer that we control all the I/O. And once we control all the I/O, we as a user can then move all of your state somewhere else. So now we can move the application from a spot to an on-demand instance and back. In fact, not only that, we can actually move, this was actually described in a paper I wrote 10 years ago called Zen Blanket. But not only that, we can migrate between different availability zones, and even at some level between different cloud providers. So here you can see availability zone in San Francisco maybe, and then one in the East Coast in Boston. So we can migrate between that. So now all of a sudden we can actually tame the spot market, and this was described in something called the super cloud. And just a little bit of background on the spot market. The price varies based off time, instance type, and then also availability zone. So we're going to want to somehow run in the cheapest zone, the cheapest instance type possible. And so what this technique is going to allow us to do, and I'm going to show this in a second, is essentially to start, at the cheapest spot at one particular time. And then if the price goes up, be able to allocate another instance and migrate it, and then get rid of the one that's more expensive or is about to go away. We did this in another paper called Smart Spot Instances for the Super Cloud. What you see here is over time, the price changes at the vertical blue lines. You can see what the cumulative price was for the different instance sizes or types. And then you can see that with this super cloud approach, we're able to achieve the lowest price possible. And not only that, we're able to in this next graph, achieve the performance. So it's very transparent. IP address is the same, no network connection is broken. We're able to do all these tricks that nobody knows that we're actually reducing the cost, and the performance is just as good. This is the web response per second, what you see down there. And then finally, does this work for real? So that was research that we've done over the last 10 years. So this is where the company or startup comes in. So the Exotanium X-Spot is a commercialization of this effort. It is reliable, it is seamless, it's plug and play like we just described, and it works on any cloud, okay? And as the last thing I have is as a case study, we have HPC workloads that run for not just hours, but days, tens of cores, hundreds of gigabytes of memory, and we're able to move it around, play whack-a-mole with up to a terabyte like it was nothing, and save up to 2/3. So this is if your costs were $1 million a year, we're shaving off 660,000, which is crazy. And then the performance overhead is essentially a noise. If it took 10 hours, it takes like 10 hours and 10 minutes. And then reliability, we're able to essentially run for months without termination. If you try to use the spot market today, you'd be lucky to run for days without being terminated, okay? And this just shows that over 2 months, we're able to achieve 0 terminations with 28 migrations. Then the last I have is essentially we show that you can then tame the spot market. This was 10 years worth of research, and that you can actually commercialize this as well. And it could be of use to the community to be able to consume the cloud and do so very efficiently. If you have any questions or want to see a demo, you can go to some of those links or send an email to me there. Okay, and then there's a paper trail there. Thank you.
Cool. Thank you so much, Hakim. That's really awesome. You're giving us at Cloud Bank some cool follow-up homework to do. So thank you again. And in true rapid lightning format, we're going to now turn to Ariel Rokem. So Ariel, please go ahead and take over.
All right, can you hear me? Can you see my slides?
Yes, on both.
Thank you. Okay, so my name is Ariel Rokem. I'm at the Department of Psychology at the University of Washington, and my group does neuroinformatics, which is work at the intersection between neuroscience and informatics. And today I'm going to talk about work done by these two people, John Cooper and Adam Ritchie-Halford. I'm going to talk a little bit about software that we develop, in particular to run very large-scale analysis pipelines in the AWS cloud using a tool that we call Cloudknot. And our main interest is studying the brain and networks in the brain that govern complex behavior, that affect development and brain health. And we do this using data from magnetic resonance imaging. Magnetic resonance imaging measures the physical properties of the brain at millimeter resolution in vivo in living humans in a way that's non-invasive. And that really opens up a lot of opportunities for research of the brain. In particular, we focus on a kind of MRI called diffusion MRI that measures the physical properties of connections between different parts of the brain that form the networks that do what the brain does. And we can measure these kinds of physical properties. And using computational tractography techniques, we can then measure and estimate the locations of connections between different parts of the brains and their physical properties. And we call that tractometry. And John Cooper, who's a research scientist in my group, has led the development, together with many others, of software called PyAFQ. That stands for Python Automated Fiber Quantification. This tool takes MRI data that we've processed and it runs it through a pipeline of steps to find, for example, in this case, the corticospinal tract, which is a connection between the brain and the spine that controls movement, or in this case, the arcuate fasciculus that connects the temporal lobe to the frontal lobe to control and understanding of spoken language and reading and things of that sort. Or here is yet another connection, the inferior frontal occipital fasciculus that connects the parts of the brain. So it automatically finds these, and then we can do what we call PASTA, which is pointwise assessment of streamlined tractography attributes. I wish I had come up with this acronym, but I didn't. That was Derek Jones and colleagues in 2005. The idea is we pick out the properties of the tissue along the length of one of these connections. For example, here is a comparison between patients with amyotrophic lateral sclerosis, ALS, Lou Gehrig's disease. This is a neurodegenerative disease that affects the motor system, And here in blue is something called fractional anisotropy, which is a property of the diffusion of water within these connections in patients with ALS, and then in red, a group of controls. And we compare this point by point, in this case, showing that the patients have lower fractional anisotropy, some change in the physical properties of their brain connections. Now, in recent years, we have entered what we might call the era of brain observatories, analogous to the telescopes that we use to look at the sky and that distribute data to everyone in the world who wants to do research on this. We have these very large studies that distribute also data. So the Human Connectome Project is one of these projects that's collected about 1,200 data from 1,200 individuals. Can another study that's collected data from 700 individuals. And these grow to be much larger. There's a very important study called the Child Mind Institute Healthy Brain Network that's collecting data from 10,000 children and adolescents. A similar very large scale study called the Adolescent Brain Cognitive Development Study is collecting also data from 10,000 children and adolescents. And these data sets provide opportunities to study at very large scale the properties of these networks. And it grows even larger. There's one data set called the UK Biobank that's going to have as many as 100,000 individuals. In particular, some of these data sets that I've highlighted here are available in the AWS through the AWS Open Data program. And so it makes sense to send our compute, our pipelines to find these connections and delineate their property to the cloud to where they are. And we're taking advantage of the AWS Batch service. Batch abstracts away the details of the infrastructure, dynamically provisions the resources that you need in order to do the job. And you can run a very, very large scale on it. But in order to do that, you have to learn new terminology, and you have to go and click through the AWS console in order to operate this thing. And so what Adam did is write a software library called Cloudknot that takes some Python code that you have running on your machine and then sends it to AWS Batch to run it on multiple different inputs, if you'd like. So this is the API of this software. You import the library Cloudknot, you install the library, you import it, and then you write some function, and then you define some infrastructure through this not object, and that does a series of operations to start all your infrastructure automatically for you in the AWS cloud. And then you can say, I would like to then map this set of infrastructure and this function to a series of arguments. For example, all the subjects in the Healthy Brain Network study, thousands of subjects in the Healthy Brain Network study. And when we do that, the operation starts on AWS Batch and the machinery goes into action, and we can then output the derivative data that we've generated into S3 and collect it from there after everything is done. To demonstrate that this works, here is a result from a recent paper. Here we did some additional modeling in order to predict the age of individuals. If you'd like to know the details, you can read this paper, tinyurl.com/brain modeling. But this is just to show that we can run this at a very large scale. Even just last week, we actually ran this on just above 2,000 subjects from the Healthy Brain Network within about a day, many, many hours of compute that ran within a day. And with that, I would like to thank the sources of funding that we have and support for this work. If you'd like to learn more about this work, you can go to the website of our group, neuroinformatics.uw.edu, read the papers. I'm happy to answer questions about Cloudknot and all of our work. So please feel free to get in touch.
All right, super, Ariel. Thank you so much. This is such a cool example of a community resource that's a byproduct of the main research you're doing. So we love this stuff. Let's see, at this point, we're going to stop recording, and we